So in summary then, the key advantage of the random walk model is that it is conceptually interesting and tractable, especially in regard to devising numerical options pricing models, and some of the early pioneers of this work won the Nobel Prize in economics. However, it's important not to view the random walk model as a purely theoretical device. So the random walk model lays the foundation of more advanced and accurate study of financial time series via widely documented stylized empirical facts. And it's important to say here that these stylized empirical facts are not a abstract mathematical model. They are a description of how real markets work, and indeed how they differ from this theoretical random walk model. So in this sense, the random walk model gives you a lens through which you can see the behaviour of real financial markets. Also, perhaps I should have said more about this, but the random walk model is also not restricted to having a normal distribution, and heavy-tailed multivariate random walk models can lead to fruitful risk management applications, including analysing contagion across different markets. Okay, so perhaps I should have given more precise references here, but these random walk models, once you add in heavy tails, can begin to give useful description of real markets. Okay, the key problem with the normal distribution models that are often used is that they underestimate the probability of extreme events. So in terms of the stylized empirical facts of financial time series, so the references here are an original research paper published in 2001 in a 3-star journal, and this book by Konstantinkov in 2004, which, whilst it's mathematically heavy going, is a genuinely applied book. So the important thing to say here is that the random walk model is not just theoretically interesting. So for instance, this Black-Scholes model can be thought of as a baseline from which stylized empirical facts are defined. So there's a sense in which the random walk model provides a lens through which you can see how real world financial markets truly behave. Now, as part of that, financial time series are widely studied, are obviously important, and the results of these studies are widely documented because they're interesting and they are very important. And just to recap, these are descriptions of how real markets behave. It's not just a mathematical idealization. The results of these studies lead to something called stylized empirical facts. So these discuss how historical data means real stock market prices truly behave, and this is a description of practical financial markets, not just a mathematical idealization. So let's list stylized empirical facts then. So this is something I've set on exams and coursework in the past, and I was thinking very clearly that I might set something like this for this year. So this list of stylized empirical facts, whilst not exhaustive, is important for this module and for this module's assessment. So these stylized empirical facts include then heavy tails, so higher probabilities of extreme events than under the normal distribution. That's the key thing here. Log returns are approximately uncorrelated, but at the same time log returns are not independent. Volatility clustering is important, and we'll discuss Arch and Garch models in the next lecture. The central limit theorem, so the idea here is that there's a sort of smoothing out effect in that returns calculated over a longer time horizon, e.g. days, weeks, months, etc., generally become closer to a normal distribution. There's this leverage effect where the volatility is negatively correlated with asset returns, and volume is positively correlated with volatility. So I think, loosely speaking, as more people trade and the volume increases, then at the same time the price is more likely to move quite wildly. So this is the listing then, which might be very useful for coursework assignment that I. So just to recap then, these stylized empirical facts, so these are general rules rather than mathematical laws of nature, so there may be exceptions to every rule. So for instance, when I talked before, there were lots of Chinese students, so we're looking at some data from the Chinese stock market, and we found some violations of these stylized empirical facts for the Chinese stock market. So by way of a caveat then, So stylized empirical facts are typically formulated for large, efficient and liquid stock markets, usually the US, perhaps some of the larger European and Asian markets as well. Now, alongside this, you therefore may observe some differences for thinly traded, less efficient and less liquid developing and emerging markets. So the example that we've covered previously in my teaching was when we're looking at data from the Chinese stock market. It's also possible that these observations might equally well apply to non-traditional asset classes like cryptocurrencies. So it'd be quite a nice topic to set for a dissertation. To what extent do cryptocurrency prices obey the stylized empirical facts that other asset classes follow, precisely because uncertainty over their economic definition might mean that their empirical prices actually behave differently. So I wanted to say a little bit more about cryptocurrencies and stylized empirical facts. So in looking at stylized empirical facts, you're not constrained to look at cryptocurrencies, but it's a natural thing to talk around in lectures, partly because it's so close to contemporary research topic, partly also it does match my own personal research interests. So in terms of cryptocurrencies and stylized empirical facts, you'd naturally expect cryptocurrency price data to share much in common with these generic stylized empirical facts. However, there could be some important qualifications to this. So for instance, if you compare cryptocurrencies to, for example, a developing stock market index, you might variously expect some autocorrelation in asset returns, and there's been some recently published empirical work on this in my former colleague's paper. You might also expect what are called very heavy tails as a reflection of extreme price risks. So it's natural that you get high probabilities of quite extreme events for cryptocurrency price data. This is true for all asset classes and is indeed one of the classical failings of the normal model of Black-Scholes, but this is especially true for cryptocurrencies. You might get very heavy tails as a reflection of just the extremely risky nature of these markets. Wanted to go through in our tests of these stylized empirical facts. So you've got some statistics here and some aspects of our programming. So in this section I want to discuss graphical and numerical tests for the stylized empirical facts 1 to 5, and this is according to the listing on page 3.2. and what I ought to say here is that when it comes to the coursework assignment for this module, make sure that you pay particular attention to the list of stylized empirical facts on slide 3.2. So we're going to go through testing the stylized empirical facts 1 to 5 in this lecture, and then stylized empirical facts 6 to 7 require separate estimates of volatility. Now, really what this requires then is a functioning derivative market. So for Bitcoin, derivative markets have recently been established. If you were looking at a stock market index or stock at this point, you would need probably some separate measures of volatility from derivatives markets in order to test these two empirical facts. But stylized empirical facts 1 to 5, you just need a sequence of observed price data. So these ones are relatively easy to check, and we'll focus on these in this lecture. So for the first one then, heavy tails. So in R, the easiest thing to do here is to test the normality of the series using the command Shapiro.test. So the null hypothesis is that the data is normally distributed, and whilst this isn't necessarily true more generally, certainly in finance, rejection of the null hypothesis would usually mean that the data has heavy tails. And what this means is just you have a higher probability of extreme events than under a normal distribution. Okay, and you get this conventional interpretation and finding if you look at the Bitcoin data. So for instance, for our Bitcoin data, if you apply this function here, Shapiro.test, to the log return series, this gives you the p-value of 2.2 times 10 to the minus 16, which is less than 0.05. So as we've seen before, you would reject the null hypothesis and conclude in this case that you've got evidence against normality, and the interpretation here from the wider financial context would be you've got heavy tails, and this would just mean a higher probability of extreme events than under the normal distribution. So we'll sort of clarify this with some graphical analysis later on, but the interpretation on rejecting a null hypothesis would be that the data's got heavy tails, this high probability of extreme events. Sort of try and show you how you see this graphically, and the useful skill here, I think, for any aspect of accounting and finance, and indeed any aspect of econometrics and statistics, will be having these cross checks. So you've got an independent source of graphical information telling you the same thing as the statistical information. So what we're trying to do here in graphing heavy tails is try and show you how the normal approximation break down, not just that the thing isn't very well described by a normal distribution. It turns out the easiest way to do this is to use something called a kernel density estimate, which is a special kind of histogram. Essentially for this course, the kernel density estimate is just a smooth histogram. Okay, so on occasion the mathematical jargon and terminology here can be a bit confusing and a bit pompous perhaps, but when we see here kernel density estimate, just think smooth histogram. So the idea is that this kernel density plot would give us your best estimate of the true probability density function of the log return, so the true probabilistic description of how the log returns evolve, and then you can sort of see how the normal distribution compares to this kernel density estimate and how the normal distribution fails. And indeed the thing to watch for here would be the if you want to do this kernel density estimate in R, then so what you would do is apply the function density to the series of returns. What this will do is produce a grid of x values over which a corresponding y value, the kernel density estimate or the histogram value, is calculated. So again, R is like a robot, it will do exactly what you tell it to do, nothing more, nothing less. And what you've got here is a sequence of commands in the background, even though you can't necessarily see any output at this point. Now the easiest thing to do is compare the y values for this histogram with the y values that would correspond to the normal distribution value. In order to do this comparison, the R function for the normal probability density is something called dnorm. So this is just the density of a normal distribution, hence the name dnorm. And in order to do this, what you need to do is match the mean and the standard deviation of the log returns. So to calculate the mean of the log returns, as we've seen before, you just need in R mean of the log return, and to calculate the standard deviation, the R command for this is SD for standard deviation. Okay, and once you've got these mean and standard deviation values, you can then use the dnorm function to see how the normal distribution compares to this fancy histogram, this kernel density estimate. So the R commands work like this then. So the first step, you plot the kernel density estimate using the x and y coordinates of the kernel density estimate. And what you've got here then, if you look at the plot command, so the dens $x is the x coordinate of this thing, and dens $y is the y coordinate, and then you specify here type equals L. So you just tell R that you want to make sure that it draws lines rather than dots. And then what you would do here is overlay a line showing the fit of the corresponding normal distribution. So to overlay a line, the R function is lines. You need the same set of x coordinates, and then the y value in this case would be the dnorm value applied to the x coordinate, and then the mean and the standard deviation of the log return series. And then after you've closed the bracket, what you've got there is the LTY stands for line type. So the idea is that this second line has a slightly different style, so you can sort of see which one is which. So the 2 points here then, you should expect to see heavier tails in financial data compared to the normal distribution, so you know precisely where the thing is going to break down as a model. And then sometimes the effect is better shown using a plot of the log density rather than the density itself.